Hi folks, so today we're going to talk a little bit about very common problems that you'll encounter in biochemistry labs where we have to prepare a buffer to a specific set of conditions. So in this question it says you have been tasked by your instructor to prepare 425 milliliters of a 250 millimolar buffer composed of sodium acetate, and the molecular weight's given, and glacial acetic acid, and a bunch of information is given here, at the specific pH of 5.4. pKa of acetic acid is 4.76. Calculate the masses of the two components you'll need and explain how you would prepare the buffer. Alright, so what we want to do here is this is a buffer problem, and if you ever are encountering a buffer problem, and you know it's a buffer problem because it says buffer in it, pretty much what you're going to have to start out with is the Henderson-Hasselbalch equation. pH equals pKa plus the common log of A over HA. Okay. Now in this case, we should first kind of spend a little bit of time talking about some of these items. So pH, of course, is the pH. We actually know that that's 5.4. That's where we want to make the buffer at, pH we want. pKa is a number set in stone. That is, in this case, 4.76. And I like to think about the pKa being kind of on a number line here. We'll go from a pH of 1 to 14, and those, remember, are the concentration of H3O plus. Okay, our pH from 1 to 14. Here our pKa is 4.76, and remember that the pKa is where the buffering agent is half in the A form, the deprotonated form, and half in the HA protonated form. If we're talking about pHs, the low pHs tend to have a lot of HA, and the high pHs tend to have a lot of A minus. Because these are, at low pHs we have a lot of H's, so it's a very high concentration, 10 to the negative 1, 0.1 molar perhaps of H plus, so we have a lot of HA. And at the high pHs we have 10 to the negative 14th molar of H plus, so it's very few H's, so we have A minus. And around that pKa, about 1 pH unit on either side, 3.76 would be one less, and 5.76, we have what's called the buffering region. Okay, so that's the area where we would be effectively having a mix of HAs and A minuses. Everywhere else are going to be either 100% HA or 100% A minus. This is the place where we are switching between A's and HAs. So are we going to have an effective buffer at this pH? Well, let's look. So here we have a pH of 5.4. That is here. I'll draw that in. Okay. That is there, 5.4. So we are in the buffering region. Now something we should take into account is, remember, at the pKa, we have a 50-50 mix of A and HA. So at this range, we should have more A than HA, because we are at a pH that is above the pKa. If we were a pH below the pKa, we would have more HA than A minus. So that's something we should predict, because it's going to come in handy when we check ourselves here in a little bit. Okay, so we are going to have an effective buffer because we are within 1 pH unit of the pKa. We are here at the upper end, so this will be an effective buffer. So that's the first thing you want to check. If it's outside that region, you'd know that it's pretty much all A or all HA, and it wouldn't be a buffer. So we have to be within 1 pH unit. Okay. So in this case, let's start working from our Henderson-Hasselbalch equation. pH equals pKa plus the log of A over HA. Now, which one of these is A and which one is HA? Well, we have two components here. We have a sodium acetate and acetic acid. Now, sodium acetate has a sodium, and a plus, and it has to have a negative too. And this is our acetate ion. So our sodium acetate is our A minus. Our acetic acid has an H. It's an acid, right? Acids give up H's. HOAC. And so you can see that if we call OAC the A minus, that this is HA. So acetic acid is the HA. It has the H's. It's an acid. the acid form, the protonated form. A sodium acetate has a sodium, which means that it must be negative on the other side, A minus. So A minus is our sodium acetate, and HA is our acetic acid. Cool. So let's start working this out. We can start doing some solutions here. pH equals pKa plus the log of A over HA, and again, we know which ones those are now. And so let's plug our stuff in. 5.4 is the pH we want. It's in the buffering region, around 4.76, plus the log of A over HA. How do we start solving this? Well, let's subtract our 4.76 from both sides. Okay, 4.76 subtracted from 5.4 ends up giving us 0.64. And that equals the log of A over HA. Cool. How do we undo common log? We raise both sides to the 10. 10 to the both sides. 10 to the 0.64 and 10 to the log. That'll cancel. And so what we get here is a nice ratio. 10 to the 0.64 is 4.365. Is equal to the ratio of A over HA. Do we have more A than HA? Yeah, we have 4.365 over 1. We have 4.365 A's for every 1 HA. So again, our intuition about the upper end of the buffering region tells us we should have more A, and we do see that here in this solution. Sometimes it's easy to forget that there's a plus here, and if you had done a minus, you'd have the backwards, and so your intuition could save you. Alright, so let's move from there. That's one piece of information we need. So I'm gonna write that down again. 4.365 is equal to the ratio of A over HA. Now here, if you notice, we have two unknowns, and so we need to solve for one of them in order to isolate the other. The other thing we know from our stem of our question is we need a 250 millimolar buffer. Nice thing about this is 250 is the sum of A and HA. It always is that way no matter what you're working on. If you're ever given a buffer concentration, it's always the two pieces in the buffering pair. So 250 millimolar is the total sum of both A and HA, and it should be heavily towards the A with not very much HA. We know 4.365 times more A than HA. So what I like to do here is I'll solve for one of the two. It's easy for me just to subtract HA from both sides. So we get A is equal to 250 minus HA. And then I'm going to plug that in up here. So 4.365 is equal to 250 minus HA over HA. Okay, I'm going to multiply by HA on both sides to get it out of here. Okay. So we get 4.365 HA is equal to 250 minus HA. Now what we can do is add HA to both sides to cancel there. 5.365 HA, because remember HA here is just 1 HA. 1 HA plus 4.365 HA is 5.365 HA equals 250. We can simplify here by dividing by 5.365. That'll cancel on this side, and then we'll have it divided by on that side. 250 divided by 5.365 is equal to 46.59. And remember, that is in millimolar. So there's one of our solutions there. HA is equal to 46.59 millimolar concentration in this buffer. How do we know our HA? Well, we already, or A minus, that is this piece, 250 minus. And so if we do 250 minus 46.59, we end up with A minus, which is 203.4 millimolar. Now, if we were to divide these by each other, 203.4 and 46.59, it better come out to be 4.365. So I'm going to check. 203.4 divided by 46.59. Okay, exactly right. 203.4 divided by 46.59 is equal to 4.365, which remember was our ratio of A to HA. So we have more A, just like we thought, than HA, and it's 4.365 times more. Okay? So those two important numbers are the concentrations. Is that what this question is asking? This question is asking to calculate the masses of the two components. So we better do that. So I'm going to write this down. HA was 46.59 millimolar, and A was 203.4 millimolar. And we did that by solving two equations, two unknowns for one of them, and then getting the other from the minus the total. So 205 minus this was this. So how do we get the masses? Well, a bunch of information is given up here. I'm going to start with the easy one, sodium acetate, which is given in molecular weight. Which one is sodium acetate? Well, it says sodium, which means that there's a negative on the acetate, which means that's this one. This is our sodium acetate. So I'm going to start with that number, 203.4 millimolar, which is the same as millimoles per liter. Okay, that's our concentration. Now we need to know how many liters we're trying to make. We're trying to make 425 mils. So 425 mils divided by 1,000 would be 0.425 liters. That's how much buffer we're trying to make. We're not trying to make a whole 1 liter here. We're only trying to make 42.5% of 1. So that's going to cancel our liters. That's going to tell us how many total millimoles. Now, what else are we given about sodium acetate? It is 82.03 grams per mole. And that's in moles. We're in millimoles here, so we need to get to moles. So we have 1,000 millimoles in 1 mole. And then it was 82.03. I'll make that nicer. 82.03 grams per 1 mole. Oops, that's backwards. I want to cancel moles. 1 mole is 82.03 grams. So let's make sure our units cancel. Millimoles cancel here, moles cancel here. We are left in grams, which is the mass we're asked for. So we can solve this. I'm going to plug it into my calculator here. 203.4 times 0.425 divided by 1,000 times 82.03. Looks like we're going to need 7.09 grams of sodium acetate in this buffer. That's one of the things. Okay, so that's done. Check. Okay, so we know the other thing too we have to solve. We got our A minus is done. Now we need to figure out our HA. So our HA is 46.59 millimolar. And our HA, remember, is acetic acid. So let's start with that number, 46.59 millimoles per 1 liter. How many liters? Remember, it was 0.425 liter to liter. And now we're in millimoles. Probably going to want to go to moles. And then what else do we know? Okay, that started exactly the same as the last one. What else do we know about acetic acid? We have a density, which is grams per mil. Right now we would be in, let's check, millimoles are canceled in moles. We have a concentration of 17.4 molar, which is moles per liter. So I'm going to do that, 17.4 mole per 1 liter. That's a molar unit. I want to do that way so the moles will cancel. Now we're in liters. And I'm just going to wrap this. So liters, our only other thing is in milliliters here. We're trying to get to grams. So I'm going to do 1 liter on the bottom, and 1,000 mils on the top. And then I'm going to put my 1 mil on the bottom. And what do we have? 1.05 grams per mil. So 1.05 on the top. Okay, so let's make sure our units will cancel. Liters cancel here, mils cancel here. We're left in grams, which is what we want. So I'm going to plug this in, 46.59 times 0.425 divided by 1,000 times, or divided by 17.4 times 1,000 times 1.05. We get 1.195 grams of acetic acid. Okay, So that is going to be our solution to that. We had 7.09 grams of sodium acetate and 1.19 grams of acetic acid. This same process is going to work for any buffer you're trying to make, as long as you're picking the right pKa, as long as you're picking the right one. So it'll be easy. So the last part of that question was telling us to explain it. So we had sodium acetate. We had 7.09 grams. So what are you going to do? Well, you're going to go to the scale and weigh that out. Okay, that's easy because it's a powder. You just put it in a weighing boat and weigh it. Then we had acetic acid. And we had, what, 1.195 grams. That's also going to be weighed. Now, acetic acid is a liquid, and so you're just going to use a dropper for that. You're just going to weigh it into that, and you're going to add to the sodium acetate. So now we have the amounts of both of our buffering pieces. What else we need to do? The last thing we need to do is add water. And where do we want to end up? To 425 mils. Final volume. Okay, that is how we'll make our buffer. So what you're going to do is get your 7.091 grams of sodium acetate, or 1.195 grams of acetic acid. Then you're going to add those together and add water until you get to 425 mils final volume. Usually you'll also want to stir to dissolve. In our biochem lab, we'll put that into a bottle, put it into the fridge and label it, and then you'll be done. So that is how you do basic buffer calculations. Hope that helps.